Behold, a marvel unfolds within the very vessel of your being, even as your gaze fixes upon this screen. A symphony of unseen forces, a dance of particles, so minuscule, so fleeting, that they seem to belong to a realm beyond the grasp of ordinary understanding. The realm of quantum mechanics, a domain of paradox and possibility, where the very fabric of reality warps and shifts with each observation, each interaction. And it is here, within the intricate architecture of your brain, some daring scientists propose that consciousness itself takes root, blooms, and flourishes, not as a mere byproduct of chemical reactions, nor as a simple electrical storm, but as a direct manifestation of these quantum principles, these unfathomable laws governing the tiniest components of existence. Imagine, if you will, the 86 billion neurons firing within your skull, not just as nodes in a complex network, a biological computer churning out thoughts, but as miniature quantum processors, each operating according to principles that defy classical intuition, each capable of existing in multiple states simultaneously, a superposition of potential realities that collapse into a single, defined experience only through the act of conscious awareness itself. This, then, is the central thesis of quantum consciousness, that the very essence of your being, your subjective experience, your sense of self, is inextricably linked to the quantum world, a world of entanglement, superposition, and wave function collapse, a world where the observer is not merely a passive witness, but an active participant in the unfolding of reality. But tread cautiously, for this is treacherous territory, a battleground of ideas where titans of science clash and the very nature of existence is at stake. Other researchers, equally esteemed, equally brilliant, scoff at this notion, dismissing it as utter folly, a fantastical notion cloaked in scientific jargon. They argue vehemently that quantum effects simply cannot survive the tumultuous environment of the brain, the warm, wet, noisy realm where particles are constantly colliding, where coherence is fleeting, and where quantum superpositions would collapse in the blink of an eye, far too quickly to have any meaningful impact on the ponderous processes of consciousness. The brain, they insist, is a classical system, a biological machine governed by the familiar laws of chemistry and electricity, and any attempt to invoke quantum mechanics is simply a desperate attempt to paper over our ignorance, to fill the gaping void in our understanding of the mind with mystical speculation. So, who is right? Is consciousness truly a quantum phenomenon, a manifestation of the universe's deepest secrets? Or is it merely wishful thinking, a seductive fantasy dressed up as scientific theory, a quest for the arcane that will inevitably lead us astray from the true path of understanding? Prepare yourself for a journey into the heart of this debate, a voyage into the uncharted territories of neuroscience and quantum physics. We shall delve into the claims that your brain operates like a quantum computer, processing information in ways that defy classical limitations. We shall explore the possibility that your thoughts exist in multiple states simultaneously, a superposition of potential realities waiting to be realized. We shall even confront the audacious notion that consciousness itself might be fundamental to the universe, a property inherent in the very fabric of reality. But be warned, this is not a journey for the faint of heart. It will challenge your assumptions, question your beliefs, and perhaps even force you to reconsider everything you thought you knew about the nature of your own mind. And as we begin, I implore you, embrace the uncertainty, embrace the paradox, and embrace the possibility that the answers we seek lie beyond the boundaries of our current understanding, in a realm where the familiar laws of physics give way to something far more profound, far more mysterious. For it is in this realm, the realm of quantum entanglement and conscious awareness, that the true nature of reality may ultimately be revealed. The year was 1989, a seemingly unremarkable date, yet within its unassuming embrace lay the seeds of a scientific revolution. A revolution not of arms and armies, but of ideas and intellect. A revolution that would challenge the very foundations of our understanding of consciousness. igniting a debate that continues to rage to this day. In that year, a British physicist, a man of unparalleled intellect and unwavering conviction named Roger Penrose, unleashed a literary bombshell upon the world. His book, a dense, challenging tome brimming with complex mathematics and philosophical speculation, dared to question the prevailing orthodoxy, to suggest that something fundamental was missing from our understanding of the mind. Penrose, a Nobel laureate and one of the most respected mathematicians alive, was not a man prone to hyperbole or unfounded speculation. He was a rigorous thinker, a meticulous researcher, and his pronouncements carried considerable weight within the scientific community. And yet, the claim he made in his book was nothing short of audacious. He argued, with meticulous precision and mathematical rigor, that human consciousness could not possibly emerge from the principles of classical physics alone. The brain, he insisted, was not simply a biological computer processing information according to the deterministic laws of Newtonian mechanics. It was something far more profound, something far more mysterious. It was tapping into the realm of quantum mechanics, harnessing the bizarre properties of the subatomic world to generate the rich, inner world of subjective experience that we all possess. Consider, for a moment, the sheer complexity of your own conscious experience. Right now, as you engage with these words, you are not merely processing visual information from this screen. You are experiencing qualia, the raw, subjective sensations that make up the fabric of your awareness. The redness of red, the sweetness of sugar, the ache of longing. These are not mere data points to be processed, but vivid, felt experiences that defy objective description. Classical computers, for all their processing power, are utterly devoid of this inner life. They can manipulate data with breathtaking speed and accuracy, but they do not experience anything. They have no sense of self, no awareness of their own existence, no inner movie playing in their heads like the one you are experiencing right now. This, Penrose realized, presented a fundamental problem for classical theories of consciousness. If consciousness is simply the result of neurons firing in patterns, like a biological computer executing a program, then why should there be any inner experience at all? Why shouldn't we all be philosophical zombies, processing information perfectly but experiencing nothing, devoid of subjective awareness, empty vessels performing complex computations without any sense of what it is like to be alive? This, the hard problem of consciousness, had stumped philosophers and scientists for centuries, a seemingly insurmountable obstacle to any purely physicalist account of the mind. But Penrose, ever the iconoclast, had a radical solution. He proposed that consciousness emerges from quantum processes occurring inside the microtubules of neurons. These microtubules, tiny protein structures that form the cytoskeleton of cells, are the scaffolding that gives neurons their shape and structure. And Penrose suggested that they might be far more than mere structural supports. They might be quantum computers operating inside our heads, harnessing the bizarre properties of the quantum world to generate conscious experience. The idea was audacious, bordering on heresy. Quantum mechanics describes a world where particles can exist in multiple states simultaneously, a superposition of potential realities that collapse into a single defined state only through the act of observation. It is a world where observation affects reality, where the very act of measurement changes the outcome of an experiment. It is a world where distant particles can be mysteriously connected through quantum entanglement, linked by an invisible bond that transcends space and time. If consciousness really does emerge from quantum processes, it would mean that your thoughts follow fundamentally different rules than the classical world around you. It would mean that your mind is not simply a biological machine, but a quantum instrument capable of harnessing the unfathomable power of the subatomic world. But Penrose faced a major problem. He was a mathematician, not a neuroscientist. He possessed the mathematical rigor to formulate his theory, but he lacked the biological expertise to ground it in the reality of the brain. He needed someone who understood how the brain actually works, someone who could translate his abstract mathematical concepts into concrete biological mechanisms. And it was then, by chance, perhaps by fate, that he met Stuart Hameroff, an anesthesiologist with a keen interest in the mysteries of consciousness. Their collaboration would produce one of the most controversial theories in modern science, a theory that would challenge the classical citadel and spark a debate that continues to rage to this day. Stuart Hameroff, an anesthesiologist by trade, was not your typical scientist. His mind was a crucible of curiosity, constantly churning with questions about the nature of consciousness, the mysterious phenomenon that he manipulated with such precision in the operating room. As an anesthesiologist, he had spent years studying how consciousness could be switched on and off with chemicals, how the very essence of subjective experience could be extinguished with the introduction of a simple molecule into the bloodstream. And he noticed something peculiar, a pattern that hinted at a deeper truth about the nature of consciousness. Anesthetic drugs, he observed, seemed to target the same microtubules that Penrose had identified as potential quantum computers. This was not a coincidence, Hameroff realized. If consciousness really does emerge from quantum processes in microtubules, then anesthetics must work by disrupting these quantum effects. When you go under anesthesia, you don't just lose the ability to respond to stimuli, you lose consciousness entirely. Your inner experience vanishes completely, as if a switch has been flipped, extinguishing the light of awareness. This, Hameroff reasoned, suggested that consciousness might indeed depend on delicate quantum processes that anesthetics disrupt. He envisioned the microtubules not just as simple structural components of neurons, but as intricate networks of quantum processors, each capable of existing in multiple states simultaneously, each interconnected through quantum entanglement, forming a vast unified field of consciousness. Anesthetic drugs, he proposed, work by interfering with this quantum entanglement, disrupting the delicate coherence that allows microtubules to function as quantum computers. When the quantum coherence is disrupted, consciousness vanishes. When the drug wears off and quantum coherence returns, consciousness resumes. Hameroff's biological insights provided the missing piece of Penrose's puzzle, grounding his abstract mathematical theory in the concrete reality of the brain. Together, Penrose and Hameroff developed what they called orchestrated objective reduction, or ORC-OR, a theory that proposed that consciousness emerges when quantum information processing in microtubules reaches a critical threshold, causing the quantum system to collapse into a specific state. This collapse, they argued, corresponds to a moment of conscious experience, the subjective feeling of being aware of something. According to ORC-OR, your consciousness is not generated by the firing of individual neurons, nor by the complex interactions of neural networks. Instead, it emerges from quantum computations occurring simultaneously across millions of microtubules throughout your brain. These quantum processes allow for non-local correlations, meaning that different parts of your brain can be quantumly entangled, creating the unified field of consciousness that you experience right now. Imagine, if you will, the vast network of microtubules in your brain as a quantum orchestra, each microtubule playing its own note, each interconnected through quantum entanglement, creating a symphony of consciousness. Anesthetic drugs, in this analogy, are like dissonant chords that disrupt the harmony, silencing the music of awareness. The implications of ORC-OR are staggering. If consciousness is quantum mechanical, it means that your thoughts might exist in superposition before collapsing into specific ideas. It could explain the creativity and intuition that seem to emerge from nowhere, the way solutions to complex problems sometimes appear fully formed in your mind, as if they had been gestating in the quantum realm before suddenly surfacing into conscious awareness. It might even suggest that consciousness has been woven into the fabric of the universe since the Big Bang, a fundamental property of reality that has been unfolding since the dawn of time. But here is where the controversy explodes. The moment Penrose and Hameroff published their theory, the scientific establishment launched a devastating counterattack. Leading physicists and neuroscientists lined up to demolish ORC-OR, arguing that quantum effects simply cannot survive in the warm, noisy environment of the brain. The battle lines were drawn, the gauntlets were thrown down,
and the debate over quantum consciousness began in earnest, a debate that continues to rage to this day, challenging the very foundations of our understanding of the mind and the universe. The heart of the scientific counterattack against ORCOR lay in a fundamental principle of quantum mechanics called decoherence. In the quantum world, particles can exist in multiple states simultaneously, a phenomenon known as superposition. A single electron, for example, can be in two places at once, spinning both clockwise and counterclockwise, existing in a probabilistic haze of potential realities. But this delicate quantum superposition is extremely fragile. Any interaction with the environment causes the quantum system to decohere, collapsing into a single defined state. Imagine, if you will, a perfectly balanced coin spinning in the air, a superposition of heads and tails. The slightest breeze, the faintest vibration will cause the coin to topple, collapsing into one state or the other. Similarly, any interaction with the environment causes a quantum system to decohere, collapsing its superposition and forcing it to choose a single defined reality. And this, the critics argued, is the fatal flaw in ORCOR. Your brain operates at body temperature, around 98.
6 degrees Fahrenheit. It's packed with water molecules, ions, and electromagnetic fields, a chaotic soup of thermal energy. According to quantum physicists, this warm, wet, noisy environment should destroy quantum coherence in femtoseconds. That's quadrillionths of a second. That's far too fast for quantum processes to influence consciousness, which operates on timescales of milliseconds, thousands of times slower. Max Tegmark, a physicist at MIT, famously calculated that quantum coherence in brain microtubules would last approximately 10 to the minus 13 seconds. To put that in perspective, consciousness operates roughly 10 trillion times slower than quantum decoherence occurs. It would be like trying to build a sandcastle while standing in a hurricane, an exercise in futility doomed to failure. The critics argued that Penrose and Hameroff were engaging in quantum mysticism, using the weirdness of quantum mechanics to paper over gaps in our understanding of consciousness. They pointed out that quantum effects, while crucial for the basic chemistry of life, operate at scales far too small and fast to directly influence the large-scale neuroprocesses that generate consciousness. The brain, they insisted, is a classical system, a biological computer governed by the familiar laws of physics, and any attempt to invoke quantum mechanics is simply a desperate attempt to salvage a flawed theory. The decoherence argument presented a formidable challenge to ORCOR. It suggested that quantum effects simply couldn't survive long enough to play any meaningful role in consciousness. The critics dismissed Penrose and Hameroff's theory as a beautiful fantasy, a seductive dream that had no basis in physical reality. And for many years, the decoherence argument seemed to be the final word on the matter, the definitive refutation of quantum consciousness theory. But the proponents of ORCOR refused to back down. They responded to every criticism with increasingly sophisticated arguments, searching for ways to circumvent the decoherence damnation, to find loopholes in the laws of physics that would allow quantum effects to persist long enough to influence consciousness. And some recent discoveries began to shift the debate in unexpected directions, offering glimpses of hope for the quantum consciousness theorists and challenging the seemingly insurmountable barrier of decoherence. The first breakthrough came from an unlikely source: photosynthesis, the process by which plants convert sunlight into chemical energy. For decades, scientists assumed that photosynthesis occurred through purely classical processes. When a photon of light strikes a chlorophyll molecule, it excites an electron, creating an exciton, a packet of energy that needs to find its way to the reaction center where photosynthesis occurs. Classical physics suggested that this exciton would randomly bounce around the leaf until it eventually found its target, a slow and inefficient process. But in 2007, researchers discovered something remarkable. Photosynthesis actually relies on quantum coherence to achieve its remarkable efficiency. The exciton exists in a quantum superposition, simultaneously exploring all possible paths through the leaf. This quantum exploration allows it to find the most efficient route to the reaction center, explaining why photosynthesis is nearly 100% efficient.
The process relies on quantum coherence lasting for hundreds of femtoseconds, far longer than previously thought possible in biological systems. This discovery shattered the assumption that quantum effects can't persist in warm, noisy biological environments. If plants can maintain quantum coherence long enough for photosynthesis, maybe brains can maintain it long enough for consciousness. The evidence kept mounting. Researchers discovered quantum effects in bird navigation, where quantum entanglement in certain proteins allows birds to see magnetic fields. They found quantum tunneling in enzyme catalysis, where particles teleport through energy barriers that should be impossible to cross classically. Even smell might depend on quantum mechanics, with molecules identified by their quantum vibrational signatures rather than just their shape. Biology, it turns out, is quantum mechanical at its core. Life doesn't just tolerate quantum effects, it harnesses them for crucial biological functions. This revelation has forced scientists to reconsider whether quantum processes might indeed play a role in consciousness. If simple organisms can evolve quantum protective mechanisms, perhaps the human brain has evolved similar strategies. The 3.8 billion years of evolution might have produced molecular machinery sophisticated enough to maintain quantum coherence in neural tissue. The discoveries in photosynthesis and bird navigation provided a glimmer of hope for quantum consciousness theorists. They showed that quantum effects could indeed survive in warm, noisy biological environments. But the critics remained skeptical. They argued that these quantum effects were limited to specific biological systems with specialized molecular structures designed to protect quantum coherence. The brain, they insisted, was a different story. It was too complex, too chaotic, too warm for quantum effects to have any significant influence. But the mounting evidence that biology was fundamentally quantum mechanical couldn't be ignored. It forced scientists to reconsider the assumption that the brain was purely a classical system, and it opened the door to new possibilities for understanding how consciousness might emerge from the quantum realm.
The quantum consciousness debate goes far deeper than just biology. It touches on fundamental questions about the nature of reality itself. Some interpretations of quantum mechanics suggest that consciousness plays a special role in the physical universe, that observation by conscious beings actually causes quantum wave functions to collapse. This idea traces back to the early pioneers of quantum mechanics. Werner Heisenberg, one of the theory's founders, argued that quantum mechanics doesn't describe an objective reality independent of observation. Instead, it describes our knowledge about reality, knowledge that changes when conscious observers make measurements. The famous double-slit experiment seems to support this view. When electrons pass through two slits, they create an interference pattern, showing they went through both slits simultaneously. But when we observe which slit each electron passes through, the interference pattern disappears. The act of conscious observation appears to change physical reality. This has led some physicists to propose that consciousness isn't produced by the brain, but is instead a fundamental feature of the universe itself. In this view, the brain doesn't generate consciousness, but rather acts like a radio, tuning into conscious experiences that exist at the quantum level of reality. This is a radical idea that challenges our most basic assumptions about the relationship between mind and matter. It suggests that consciousness isn't simply a byproduct of brain activity, but is a fundamental aspect of the universe that interacts with matter in ways we don't yet fully understand. But the observer effect interpretation of quantum mechanics is highly controversial. Most physicists prefer interpretations that don't require conscious observers to play a special role in the physical universe. They argue that the collapse of the wave function occurs through interactions with any measuring device, not just conscious observers. The measuring device simply needs to become entangled with the quantum system, forcing it to choose a single defined state. The observer effect interpretation also faces the problem of circularity. If consciousness is required to collapse the wave function and create reality, then how did consciousness itself arise in the first place? The answer might lie in panpsychism, the idea that consciousness is a fundamental property of all matter. In this view, even simple particles might possess tiny amounts of consciousness, proto-consciousness, that combine to form more complex conscious experiences in brains and other biological systems. The quantum mechanics might provide the mechanism for this combination, allowing billions of tiny conscious elements to bind together into your singular stream of consciousness. Integrated information theory, developed by neuroscientist Julio Tononi, takes a different approach. Instead of focusing on quantum mechanics, it argues that consciousness corresponds to integrated information in any system. The more integrated information a system contains, the more conscious it becomes. Integrated information is defined as the amount of information that a system possesses above and beyond the sum of its parts. A heap of sand, for example, has very little integrated information because each grain of sand is independent of the others. A brain, on the other hand, has a vast amount of integrated information because each neuron is connected to thousands of other neurons, forming a complex network that processes information as a whole. Tononi has developed mathematical measures of integrated information, called phi, that attempt to quantify the amount of consciousness in a system. The higher the value of phi, the more conscious the system is. This theory suggests that consciousness exists on a spectrum. Humans have high levels of integrated information and therefore rich conscious experiences. But even simple systems like photodiodes might have tiny amounts of consciousness. In the most extreme version of this theory, called panpsychism, consciousness is a fundamental property of all matter, like mass or charge. If panpsychism is correct, then the particles in your brain aren't generating consciousness from nothing. Instead, they're organizing existing conscious elements into the complex unified experience you call your mind. Quantum mechanics might provide the mechanism for this organization, allowing billions of tiny conscious elements to bind together into your singular stream of consciousness. These ideas sound like science fiction, but they're being seriously debated by leading scientists and philosophers. The reason is simple. Traditional neuroscience has made remarkable progress in understanding how the brain processes information, but it's made virtually no progress in explaining why there should be any subjective experience at all. We can map neural networks, trace how information flows through the brain, and even predict some thoughts based on brain activity. But none of this explains why you experience the redness of red, the pain of heartbreak, or the joy of discovery. The hard problem of consciousness remains as mysterious as ever. This explanationary gap has convinced some researchers that consciousness requires physics beyond our current understanding. Just as quantum mechanics was needed to explain phenomena that classical physics couldn't handle, perhaps consciousness requires new physical principles that we haven't discovered yet. But skeptics argue that this is premature. Neuroscience is still a young field, and our understanding of the brain is advancing rapidly. They point to recent discoveries about neural networks, predictive processing, and global workspace theory as evidence that consciousness will eventually be explained through purely classical mechanisms. The debate has practical implications too. If consciousness really is quantum mechanical, it could revolutionize medicine, artificial intelligence, and our understanding of mental illness. Quantum consciousness theories suggest that depression, schizophrenia, and other psychiatric conditions might result from disrupted quantum processes in the brain. Some researchers are already exploring quantum-based treatments for mental illness. Transcranial magnetic stimulation, which uses magnetic fields to influence brain activity, might work by affecting quantum processes in neurons. Even meditation and psychedelic experiences might involve quantum effects, potentially explaining their profound impact on consciousness. The AI implications are equally profound. If consciousness requires quantum processing, then creating truly conscious AI might require quantum computers rather than classical ones. This could explain why current AI systems, despite their impressive capabilities, seem to lack genuine understanding or subjective experience. But we're getting ahead of ourselves. Before we can explore these implications, we need to examine the evidence more carefully. Is there really proof that quantum effects can survive in the brain? What do the latest experiments reveal about microtubules and quantum coherence? And how do mainstream neuroscientists explain consciousness without invoking quantum mechanics? The answers to these questions will determine whether quantum consciousness theory represents a revolutionary breakthrough or an elaborate scientific mistake. The stakes couldn't be higher because they involve nothing less than our understanding of what it means to be conscious, to be human, to experience the world from the inside. As we dive deeper into this controversy, remember that science progresses through exactly these kinds of heated debates. The most important discoveries often emerge from ideas that initially seem impossible or absurd.
Whether quantum consciousness theory falls into that category remains to be seen, but one thing is certain: this debate is forcing scientists to confront the deepest mysteries of mind and reality. In doing so, it might just revolutionize our understanding of both. The revolution began in a laboratory at the University of California, Santa Barbara in 2010. For the first time in history, scientists created a quantum object visible to the naked eye. They took a tiny mechanical resonator, a piece of metal smaller than a human hair, and cooled it to near absolute zero. At that temperature, something extraordinary happened. The resonator began vibrating and not vibrating simultaneously, existing in a quantum superposition of motion and stillness. This breakthrough shattered a fundamental assumption about quantum mechanics. For decades, physicists believed quantum effects were confined to the microscopic world of atoms and particles. Larger objects, they insisted, were too big and too warm to exhibit quantum behavior. But the Santa Barbara experiment proved that quantum mechanics could operate at scales approaching the everyday world. The implications for consciousness research were immediate and profound. If a mechanical device could maintain quantum coherence at relatively large scales, perhaps the brain's microtubules could too. Stuart Hameroff seized on this discovery, arguing it vindicated his collaboration with Roger Penrose. Maybe consciousness really could emerge from quantum processes in the brain. But the skeptics weren't convinced. They pointed out crucial differences between the laboratory conditions and the brain's environment. The mechanical resonator required near absolute zero temperatures and complete isolation from environmental noise. Your brain operates at body temperature in a soup of chemicals, ions, and electromagnetic fields. The conditions couldn't be more different. Yet something strange was happening in biological laboratories around the world. Researchers studying quantum effects in living systems were making discoveries that defied conventional wisdom about biological quantum mechanics. The evidence was mounting that nature had learned to harness quantum effects in ways that seemed impossible according to traditional physics. In 2013, scientists at MIT discovered quantum effects in the light harvesting complexes of marine algae. These organisms live in one of the noisiest environments on Earth, constantly buffeted by water molecules and thermal fluctuations. Yet they maintain quantum coherence for hundreds of femtoseconds, long enough to achieve remarkable efficiency in capturing and transferring light energy. The secret, researchers found, lies in the precise architecture of biological molecules. Evolution hasn't just tolerated quantum effects, it has optimized molecular structures to protect and exploit quantum coherence. Proteins fold into specific shapes that create quantum-friendly environments, shielding delicate quantum processes from environmental noise while allowing them to function. This discovery sparked a new field called quantum biology, and its findings have profound implications for consciousness research. If simple organisms can evolve quantum protective mechanisms, perhaps the human brain has evolved similar strategies. The 3.8 billion years of evolution might have produced molecular machinery sophisticated enough to maintain quantum coherence in neural tissue. Anirban Bandyopadhyay, a quantum physicist at the National Institute for Material Science in Japan, decided to test this hypothesis directly. His team began studying the electrical properties of microtubules extracted from brain tissue. What they found astonished the scientific community. Microtubules, it turns out, are far more complex than anyone had imagined. They don't just provide structural support for neurons, they form intricate networks capable of processing and storing information. When Bandyopadhyay's team applied electrical fields to microtubules, they observed resonant frequencies that suggested quantum-scale information processing. The microtubules exhibited what physicists call coherent oscillations, synchronized vibrations that could only be explained by quantum mechanical effects. Even more remarkably, these oscillations persisted at room temperature, exactly the conditions found in living brain tissue. The implications were staggering. The brain might indeed contain quantum computers operating inside every neuron. But the most shocking discovery came when researchers realized that microtubules are connected throughout the brain in vast networks. Unlike classical computers that process information sequentially, these quantum networks could perform massive parallel computations, processing billions of quantum states simultaneously. If consciousness emerges from this quantum processing, it would explain the brain's remarkable computational abilities. Consider what your brain accomplishes right now as you watch this video. You're simultaneously processing visual information, understanding language, accessing memories, generating emotions, and maintaining awareness of your surroundings. Classical computers struggle to perform even one of these tasks well. Yet your brain handles all of them effortlessly, while using less energy than a light bulb. Quantum consciousness theorists argue that this computational power can only be explained by quantum processing. Your brain isn't just a classical computer made of biological parts, it's a quantum computer that exploits the strange properties of quantum mechanics to its extraordinary capabilities. The theory received unexpected support from an unusual source: anesthesiology research. Noble gases like xenon and argon can induce anesthesia even though they're chemically inert. They don't bind to receptors or interfere with neural chemistry in any obvious way. Yet they can eliminate consciousness completely, suggesting they might disrupt quantum processes rather than classical neural activity. Researchers discovered that these gases have a peculiar property. They can dissolve into the lipid membrane surrounding microtubules, potentially interfering with quantum coherence. The concentrations required for anesthesia correspond precisely to the amounts needed to disrupt quantum processes in microtubule networks. This correlation isn't coincidental, quantum consciousness theorists argue. It provides direct evidence that consciousness depends on quantum effects in microtubules. When anesthetics disrupt these quantum processes, consciousness vanishes. When the anesthetics wear off and quantum coherence returns, consciousness resumes. The evidence extends beyond anesthesia to other consciousness-altering substances. Psychedelic drugs like LSD and psilocybin might work by enhancing quantum coherence in neural microtubules, explaining their profound effects on consciousness. These substances seem to expand awareness, create synesthetic experiences where senses merge, and generate feelings of cosmic unity that mirror the non-local connections predicted by quantum mechanics. Even meditation might involve quantum effects. Advanced meditators report states of consciousness where the sense of self dissolves and awareness becomes unified with the universe. These descriptions closely match what quantum physicists would expect if consciousness really does emerge from quantum entanglement between different brain regions. Brain imaging studies of meditating monks reveal synchronized neural activity across widely separated brain areas, exactly what quantum consciousness theory would predict. The synchronization occurs too rapidly to be explained by classical neural communication, suggesting that quantum entanglement might be linking distant brain regions instantaneously. But critics remain unconvinced.
They argue that correlation doesn't prove causation, and that alternative explanations exist for all these phenomena. Max Tegmark, the MIT physicist who calculated decoherence times in brain tissue, has refined his analysis and maintains that quantum effects cannot survive long enough to influence consciousness. Tegmark's calculations focus on thermal decoherence, the way heat destroys quantum superpositions at body temperature. He argues thermal vibrations are so violent that they would destroy quantum coherence in microtubules within femtoseconds. No biological mechanism could protect quantum states from this thermal assault. The quantum consciousness advocates have responded with increasingly sophisticated arguments. They point to recent discoveries about quantum error correction in biological systems, mechanisms that can protect quantum information from environmental noise. Some bacteria use quantum error correction to maintain quantum coherence in their navigation systems, suggesting that brains might have evolved similar protective mechanisms. Henry Stapp, a physicist at the University of California, Berkeley, has proposed that consciousness might involve quantum Zeno effects, where frequent quantum measurements can actually freeze quantum systems in specific states. If the brain's microtubules are constantly making quantum measurements, they might be able to maintain coherence indefinitely despite thermal noise. The debate has grown increasingly technical, with both sides marshalling complex mathematical arguments and experimental data. But at its heart, the controversy remains philosophical as much as scientific. It asks fundamental questions about the nature of mind and matter, about whether consciousness can be reduced to purely physical processes or requires something more. Neuroscientist Christoph Koch, who has spent decades studying consciousness, represents the mainstream scientific view. He argues that consciousness emerges from classical neural processes, specifically from the integration of information across different brain regions. In his view, quantum mechanics is irrelevant to consciousness because the brain operates as a classical system. Koch points to the remarkable progress neuroscience has made in understanding consciousness through classical mechanisms. Researchers can now predict with surprising accuracy what people are seeing, thinking, or remembering based solely on classical neural activity patterns. Brain stimulation can trigger specific memories or alter personality traits, suggesting that consciousness is entirely reducible to neural chemistry and electricity. The global workspace theory, developed by psychologist Bernard Baars, provides a classical explanation for how consciousness might emerge from neural activity. According to this theory, consciousness arises when information becomes globally accessible across different brain regions through classical neural networks. No quantum mechanics required. Integrated information theory offers another classical approach, proposing that consciousness corresponds to the amount of integrated information in any system. Giulio Tononi, the theory's creator, has developed mathematical measures of consciousness that depend only on classical information processing, not quantum effects. These classical theories have made testable predictions and achieved some experimental successes. They can explain many features of consciousness, from attention and memory to the unity of conscious experience. Quantum consciousness theory, critics argue, makes few testable predictions and explains little that classical theories can't handle. But quantum consciousness theorists contend that classical theories face an insurmountable problem. They cannot explain why there should be any subjective experience at all. Even if classical neural networks can process information and generate appropriate responses, why should there be something it's like to be conscious? This explanatory gap remains the strongest argument for quantum consciousness theory. If consciousness really is just classical information processing, then sophisticated computers should eventually become conscious. Yet, despite decades of advances in artificial intelligence, no computer system shows convincing signs of genuine subjective experience. Recent breakthroughs in AI have only deepened this mystery. Large language models can engage in seemingly intelligent conversations, solve complex problems, and even display apparent creativity. Yet, they show no signs of genuine understanding or consciousness. They process information brilliantly, but appear to experience nothing. Quantum consciousness theorists argue this is exactly what we should expect if consciousness requires quantum processing. Classical computers, no matter how sophisticated, cannot replicate quantum effects. Only quantum computers might eventually develop genuine consciousness, and even then, only if they implement the specific quantum processes that evolution has crafted in biological brains. The debate has attracted attention from technology companies investing billions in quantum computing research. If consciousness really requires quantum processing, then the path to artificial consciousness runs through quantum computers, not classical ones. This could reshape the entire field of artificial intelligence. But quantum computers face their own decoherence problems.
Current quantum computers must operate at temperatures colder than outer space and require elaborate error correction systems to maintain quantum coherence. If biological brains can maintain quantum coherence at body temperature, they would represent a technological breakthrough that could revolutionize quantum computing. Some researchers are already attempting to reverse engineer biological quantum coherence mechanisms. If they succeed, they might create quantum computers that operate at room temperature, potentially leading to revolutionary advances in computing power and artificial intelligence. The stakes of this debate extend far beyond academic philosophy. If quantum consciousness theory is correct, it could transform medicine, technology, and our fundamental understanding of human nature. Mental illnesses might be treated by correcting quantum processes in the brain. Consciousness might be enhanced through quantum technologies. Death might not represent the complete end of conscious experience if quantum information processing can survive biological death. These possibilities remain highly speculative, but they illustrate why the quantum consciousness debate has captured scientific and public imagination. At its heart, this controversy addresses the deepest questions about existence. What are we? How do we experience the world? What makes consciousness possible? The answers might emerge from unexpected directions. New experimental techniques are allowing researchers to probe quantum effects in biological systems with unprecedented precision. Advanced brain imaging technologies are revealing the neural basis of consciousness in ever greater detail. Quantum computers are beginning to demonstrate capabilities that might eventually approach those of conscious minds. As we stand at the intersection of quantum physics, neuroscience, and consciousness studies, we face a profound choice about how to understand the nature of mind. The quantum consciousness debate represents more than a scientific disagreement. It's a fundamental question about what it means to be human in a quantum universe.